something from there. All right. The stream has started on YouTube as well. Hello everybody. We will learn segment trees today. I mean, you will learn, I will teach. Mainly this stream will be about coding rather than explaining what segment trees are. But a very brief recap is the following. Segment tree is able to modify element of a sequence. So there is an update. Change like the fifth element to new value 100 and give me, for example, the sum of values in the range from position L to position R. Instead of the sum, this could also be range minimum query or greatest common divisor, XOR, a few other types as well. Yes, this is on YouTube as well. The idea, what's the idea? This is the idea. For a moment, let's ignore everything in yellow. There is a sequence like this one, 5, 2, 3, 3, 4. For simplicity, we add zeros at the end. And if somebody asks me about the sum of 4 consecutive elements, then it would be nice to maybe very efficiently answer that. Just like with what we did before sparse table. We will do something special for powers of 2. So maybe I will pre-compute that the sum here of this range is, what is it, 13. Maybe I will also pre-compute that the sum here is 4, and the sum of everything is 17. Maybe something like that. And thanks to this, I will be able to answer queries faster. What's the sum in an interval? But the whole sequence can be of big size, like 1 million, and it's not then enough to store what happens for 4 consecutive values or 8 consecutive values or everything. It needs to be, I need to do something for every power of 2. And for that, I will store what's the sum of first 2 elements, 7, next 2 elements, that's 6, here 4, here 0, then the sum of those is 13, sum of this is 4, and sum of everything is 17. And if somebody asked me, let's say, about the prefix, this is just everything until the end, about the prefix of the sequence, they say, give me the sum of those 3 elements, or give me the sum of those 5 elements. Then I can answer that in logarithmic time. Can you add pop-out chat link to YouTube description? I won't bother now, sorry. They tell us, give me the sum of this, then I can do that quite easily, because I can grab this 7, which represents the sum of those 2 elements, and I can take this 3. Or in general, which might be useful here, here we have a very long sequence with 16 indices. The indices are in blue, and if somebody tells me now, give me the sum of values from 0 to 9, then I will give them a sum that I store for the first 8 elements. So this is represented by one part of a segment tree, this is represented by some very smaller part of a segment tree, and I will sum this up. I have a feeling that what I'm doing so far is chaotic. How do I want to talk about that? I wanted to here be very brief and focus on the implementation part. Anyway, we have a binary tree. If we create those sums bottom up of every 2 consecutive elements, and I will draw this kind of connections, I will have a binary tree. And I can move around this binary tree, and I claim that having this binary tree allows me to ask any query about the range in logarithmic time. And even more, it allows me to modify element, a leaf of this tree, which was impossible for sparse table. Sparse table was able to answer stuff in logarithmic or constant time, but we weren't able to modify anything. And now on bigger example, maybe this one first. This, we're not talking about space complexity right now. What do we have here? Let's say somebody says, give me the sum of this prefix. Then instead of going through all 6 elements and adding them one by one, I can instead grab this element. It will represent the sum of those 4. This number written here is the sum of those 4 values. And I can grab this element. It will keep the sum of those 2 values below. So the sum of these 2 is the sum of the first 6 elements. And in general, if we need the sum of first k elements, we should represent k as the sum of powers of 2. Maybe k is, in some case, 16 plus 4 plus 2 plus 1. This binary representation of k will tell us which vertices we need to take. Like here, 6 was 4 plus 2, so I first needed to take a vertex representing the first 4 elements, the sum of first 4, and then starting from this moment, I need an element representing the sum of next 2 elements. In this case, if we have some bigger segment tree, there is some vertex representing the sum of first 16 elements, and then from that moment, the end of that one, I need the sum of next 4 elements, and so on. The sum of next 4 elements, it just represents something that will be this high. And this one. This vertex, it stores the sum of 4 elements in leaves. That's the idea if we want sum of prefix. If it's a general sum, then it's more complicated than this. But for this, I think we need a bigger tree. So I will work with this big example. Let's say we are given a sequence of size 13, indexed from 0 to 12. We pad it with zeros to get size being power of 2. I added zeros here. Now I have indices from 0 to power of 2 minus 1. Then I keep building by taking 2 consecutive values and writing down their sum. 3 plus 2 is 5. Then there's 2, 3, 3, and so on. Uh, 5 and 2, they sum up to 7, 6, 8, and so on. So clearly we need to build this tree bottom up, starting from the leaves. Then I can easily know every next layer. This is 2, 10, 13, and finally sum of 13 plus 10, 23. Okay, this is a segment tree. We can build it in just time constant per every node. So what's the time of building this tree? In this case, in the last layer we had 16 nodes. In the second last layer we had 8 nodes here. Then we have 4 nodes in the next layer, 2, 1. The sum of that is 32 minus 1. Always, if you sum up consecutive powers of 2, you will get the next power of 2 minus 1. So this always, when you have some kind of n being power of 2, and that represents the size of your array, then the total size of a segment tree and the time needed to build it is just twice that. If you had an array of size 16, you need 32 nodes. So the time and space complexity to build a segment tree is linear, O of n. O of n to build. And how do we answer queries? We have a query about some range, let's say this one, from 3 to 9. The best method is to start going recursively from the root. Go from the root and always branch into two children and say, hey, you tell me if I have a query about range from 3 to 9, then in your subtree, what's the sum of values in that range? With indices from 3 to 9. But don't worry about values outside of your range. So here, this child, the child with value 13, it should tell me what's the sum of these values. So I hope that 13 will be able to recursively compute the sum of those values I marked, which is, what, 4, 7. Well, when I go to the right, here in this part, I should get 5. This is kind of divide and conquer, where if somebody asks me about the sum of values from 3 to 9, I can separately focus on the sum of values from 3 to 7 and from 8 to 9. We don't really need to think about it as divide and conquer, but we are in the root. I tell both children, hey, tell me the answer for range 3 to 9. Every such child, it also recursively goes and says, hey, give me the answer for range 3, 9, give me the answer for range 3, 9. And additionally, what happens is when we are in some vertex, like this one, and we see that the query range, the one in yellow below, from 3 to 9, it completely contains range that I represent, this whole subtree. So this, maybe that. This yellow vertex, it stores the sum of values 2, 1, 2, 1, those 4. And I need to get the sum of all of those. So from 6, instead of going down recursively, I will just get 6 as part of the answer. Node with value 6 will not go deeper recursively, and instead it will just return 6. So, I don't want this, because that's a more general pseudocode. Let's start building pseudocode then. Get, I don't know how to call it, f. F is the best name for a function. For some particular node, this will be C++, for a particular node and particular query range, let's call it query low, query high. In our case, it was from 3 to 9. Usually what we do is we return left child dot, let's say f of left child, comma query low, query high, plus f of right child. Right, nothing too interesting if we just want to always branch into both children. I don't need that big of a font. Here we go. All right, but we have some optimizations. If our range here, like this node, I know that everything below is inside, everything from 2 to 1, like 2, 1 to 1, is inside the yellow query interval. So I need to say this. If this node is completely within interval, yellow interval query low, query high, return the value stored at this node, something like node.value or node.sum. I will just keep it like that. Tree will be one big array, such that for every node I will know what is the sum stored there. This is an optimization so that I wouldn't go deeper down from 6 in this case. And also, if this node with value 7, it will go recursively to the left child with value 5, I know that that thing doesn't have below anything from range from 3 to 9. The query is about range from 3 to 9, and 5 is responsible for range from 0 to 1, so they are disjoint. Other than this, we also need to say if this node is disjoint with interval query low, query high, then return 0. That's everything we need. Just it's not trivial maybe how to implement this check and this check. Instead of some segment tree, can we build segment tree for greatest common divisor? Yes, we can. Fenwick tree, we will not discuss Fenwick trees. They can only do subset of stuff, so you should just learn segment trees and that's it. Recursive segment trees can solve everything. I don't see a reason to bother with some data structure that is still tricky to understand, but cannot do some problems. I agree, Sanat, that it's not easy to say how do we check this. But we can do it like that. When we are for every node, we can know what interval of indices it represents. Maybe this should be written in blue. This one is from 0 to 15, which means this node, the value here, 23, stores the sum of values in positions from 0 to 15. What about this left child, 13? It stores the sum from positions from 0 to 7. This guy stores the sum from positions 0 to 3. This one, 4 to 7. Because 6 is the sum of everything here, and here we have positions from 4 to 7. And like that you can for every node say what range it represents. So really when we say this node is completely within the interval, what we should say is that maybe this. If query interval is from 3 to 9 and I'm responsible for values from 4 to 7, from positions for positions from 4 to 7, then this is completely inside the yellow query, so I should just give the sum, return my value in this case. How do we check if one interval is within another? We need to say that in this case 3 small equal 4 and 7 small equal 9. Right? Then this interval for 7 is inside 3, 9. And 9 were query low, query high. Those are the two values given to us in a query. 4 and 7, those are, let's say, blue low and blue high, something like that. Node low means for this node, what's the leftmost leaf ID below me. And node high is what's the rightmost, so biggest leaf ID. How should we know that? Either we need to pre-compute it and for every node store this blue pair, or even easier, when we start recursively for a root, I can pass those two values. This is 0 and the full power of 2 minus 1, where 16 is size of this tree, 16 is the number of elements in the sequence that I start with. As I said, if it's not power of 2, I pad with zeros, so it would be power of 2. So I first run for the root with interval 0 to 15, and then later when I split into two children, I know how to split. If you tell me that there is a node and it is responsible for interval, let's say, from 8 to 15, then I can tell you what the two children are, without knowing anything else about this. 8 to 15, here the middle element between 8 and 15 is 12, and I claim from this that the left child is responsible for 8 through 11, and the right one is 12 through 15. Those are first 4 values and then next 4 values, among these all 8 values. 11 is exactly 8 plus 15 divided by 2 rounded down. This is the same thing rounded up. And always, when you know that there is some range from position I to position j, maybe I want this to be a power of 2. from I to j, then you know if you will get the average of I and j and you round it down, you will get this element just to the right of middle. And from I to I plus j divided by 2, you will have the left half. And from I plus j divided by 2, this is I plus j divided by 2, and this is that plus 1 to j, you have the right half. So node low and node high, the blue values you can pass. Pass like this. You don't need to see my face right now. And if this node is disjoint, we will do that. And how do we get down to left and right child? Last in left is this node low plus node high divided by 2. This by default rounds down. Right? This will be the last ID of the left child. Like in this drawing from I to j, that's the position of this x. The left child is responsible for interval from I to I plus j divided by 2. So from, if we computed that, then the left child is from node left, this is I, to last in left. And the right one starts at last in left plus 1 and lasts until node right. Right now you should be focusing on this part and this one. If I was from node left to node right, then my left child is until the middle of that, and my right child is from the middle to node right. And now I'm able to indeed check if I'm disjoint or I completely contain, if query interval completely contains me. How to check if this node is disjoint? We need to check if two intervals are disjoint. And they are disjoint either if this is true. So this would mean that the interval for this node is completely to the left from interval for this query, or the other way around. This would mean that the interval for this query is completely to the left from interval for this node. In that case, we return 0. And that's it. We need to also run this in the first place, starting from the root. And we need to provide, now what do we need to provide? 0, 15, where 15 stands for the power of 2 minus 1. Then query low, query high. Those are two values from the input, saying that we want to get the sum from this range. There is one last thing here that we didn't discuss. What is left and right? And here, that depends on our exact implementation. It is possible to, for example, implement all of this with pointers, and then this will be just pointer from node, like pointer to the left child. And we can also have pointer to the right child, sure. But it turns out most convenient for us, let's work on this yellow drawing, to store the whole segment tree as one big array when we say that this is index 1, then 2, 3, 4, 5, 6, 7, and so on. This numbering turns out easy to handle because of how easy it is to access children or a parent. For any vertex, like 6, your children are twice 6 and twice 6 plus 1. You can check that for any vertex here. For any x, your children are twice x and twice x plus 1. And the root is 1. So we start for the root, and here we go to the left child being twice node, and right child being twice node plus 1. This is how we start, assuming that this is power of 2 being size of the array, -1. You might say that we need to do something special for a leaf, but we don't need that, because for a leaf it must be true. A leaf will have blue interval of size just 1, like maybe leaf represents interval of indices from 5 to 5. Then either this is inside the yellow query interval or it's disjoint. If we are a leaf, then one of those two ifs must happen. Okay, now I said that it will be brief explanation on what segment trees are. It took us quite a lot of time, but at least we have some code already. I think I will just copy paste this to my IDE, and time to solve something. I think the easiest is range some queries. This problem, it has much easier solution because we can just use prefix sums. I thought that it's saved. All right. I will copy paste my code and build on the top of that. What we have here is we're given n, the size of the sequence, q, the number of queries, the array, and queries. Give me the sum in this range. Let's try to handle that. Let's read all the values in the sequence A, and while n is not a power of 2, A pushback 0 or something like that. Yeah, this will work. Later we'll see that this is unnecessary, but this is how we can pad a array A with zeros to make size to be power of 2. If the sequence size was 13, we will make it 16. And it's then very convenient that it is a power of 2. What then? I need a tree. And we saw, where do we saw it? Here. If I have a sequence of size 8, then in green here we have indices from 1 to 15. That was the case if sequence was of size 8. So for size 8 we need like size 16, array of size 16. Then I will create a tree globally, and I will set its size to twice n. For example, if the sequence size is 6, then here we make n to be 8, the next power of 2, and here then this is of size 16. So I would be able to access indices from 1 to 15. Here we need to, well, to build a tree, but then we answer queries. In every query we read, say, low and high, and they are from 1 to n in this problem. I will subtract 1 to get indices from 0 to n minus 1. Oh, pop count, good question. Pop count returns the number of ones in the binary representation of a number. Well, long story short, this is a way to check if n is a power of 2. So you can just assume that. That's not really very important for the full implementation. There are various ways to find the next power of 2. Like, this is a mini problem, sub-problem, where given 25, you would need to increase it up to 32. The question is how to get the next power of 2. And what do we do? F of, I have it here, where 15 is n minus 1. N is now a power of 2. I say that the root is 1, I run recursively for the root, and it represents in range of indices from 0 to n minus 1, so just the whole array. Low high is the query. It is passed as query low, query high. Right. I will move 3 above the function, so actually the function could access here the 3 value. And the last thing is to build a tree. Here obviously we will print this, the value returned. How do we build a tree? Well, the same order I built it, I as a human. When I had this huge drawing, I had the sequence first, this thing, and then I started to building up the next layer and the next layer. So for sure we will go with indices backwards. And it turns out to be a very good idea. Well, indices in a tree from 8 to 15, those should just be copied, values should just be copied from the array. And then from 7 to 1, everything here, every value should be taken as the sum of 2 children. And it's most convenient to do it backwards. Do it for 7, for index 7, then for index 6, 5, 4, 3, 2, 1. So, how do we build a tree? First, fill in 3 indices 8 through 15 with just, array values. Here n is 8, like in our example, in our drawing, n would be 8. We iterate through the whole array, and we put every element on proper position in the tree. And after that we go from 7 to 1. And every element, every node of a tree is the sum of 2 children. We already know how to access children. Those are 2i and 2i plus 1. And I will now remove those comments because they are confusing. Not always we have 8 and 16. Let's see if it compiles. Node, oh, I was inconsistent about node left versus node low. Yep, seems good. And I think we did. No, we did not. Overflows, I guess. Yeah, overflows. Int is not enough in this problem. We need to use long. Also, every node, if it stores the sum of all the values below, it should be long. In particular, the root contains the sum of all values in the sequence, and that exceeds 2 billion easily. We will then discuss how to make an update in 2 ways, with a recursive function and iteratively. By the way, query can also be done iteratively, but I'm not going to teach you that, because there are some problems that require harder stuff with segment trees, like lazy propagation, and then it's just much easier to do it recursively. So I will then write this down. Recursive version, let's say, can handle everything, while iterative version, which is arguably maybe in some cases easier, maybe in some cases faster, it cannot solve some problems. So if I want you to use just one version, it should be recursive. But yeah, this can be replaced with iterative stuff. CP Handbook has iterative in the basic tutorial. I understand why you might want to use iterative, but recursive is better in the long run because you can solve harder problems too, those that require lazy propagation. Okay. 2 ways to make an update. Now, let's go back to the problem set. And now we do dynamic range sum queries, where there are queries about the sum values in range from A to B, but also update the value at position K to new value U. Well, how our tree would change if I said that this value 2, actually now it's 4 instead of 2. It wouldn't change the whole tree. It would change only those values in the path to the root. Because like this 7. This is 7 because it's the sum of values below those 4 elements. Those elements didn't change. And now there are 2 ways to approach this. Either you see that, well, 2 changed up to 4, so 2 got increased by 2. So I can do +2 for every node in this path, including this leaf. That's one possibility. The other is to just update the leaf as they told us, so modify the value to a new value, whatever it's given, and then for everything in the path to the root, run the update, just like we did when building a tree. The value here, no matter what it was, it should be now 4 plus 1, so 5. The value here, it should be 3 plus 5, so 8. Then value here should be 7 plus 8, 15, and this is 15 plus 10, that's 25. It's not difficult to access the proper leaf. So we know that this position, if that's 6 or just I is given in the input, we know that in the tree, this node, it has position n plus I. We know that from this drawing. If n is 8, and we used the blue indices, 0, 1, 2, 3, 4, and so on, the value a of 3 corresponds to the leaf with position 11. 11, it's 8 plus 3. A of 0 is stored in tree of 8. This is the same as tree of 11, because that's 8 plus 3. We know what in the tree we should update. We should update tree of this. This is equal to the new value given to us. And then we go with this path to the root. If we know that child has index ID, then we know the parent has index ID divided by 2. Like if parent 6, it had children 12 and 13, then it also allows us to get from a child ID, like 12, we can get the parent ID, because we just divide by 2. With 13, we can also get parent ID, divide by 2, and round down. So iterative update is this. Change position I to a new value v. Tree of n plus I becomes v, and everything in the path, starting from the parent of n plus I, as long as we are like up to the root, and we keep dividing by 2. We update this node by using 2 children. We updated the leaf, and then this for loop updates parent of that leaf, then grandparent of that leaf, and so on. For example, if let's say n is 8, I is 3, then we modify tree of 11 as this new value v, then tree of 5 we update as tree of 10 plus tree of 11. then 3 of 2 we update as something, and so on. What happened here is we update the leaf like they told us to do, and then 5 is the direct parent of 10 and 11. It for sure was visible in the drawing. 5 is the parent of indices 10 and 11. So we need to update the value that is stored in this node, in this guy. Build isn't n log n. We explained why building is O of n. Because it's, 8 plus 4 plus 2 plus 1, this is equal to 15, so we explained why the build is linear. And also you can see in the code, building is just 2 for loops, each of size n. So how can it be slower than linear? Okay. This update, it divides by 2 multiple times. And of course, height of this binary tree is logarithmic. So the complexity of this is O of log. What we didn't explain yet is why complexity of this function is O of log. We'll get back to that later. Okay, now let's apply this to the program dynamic range sum queries. Every query, it has some type. Type 1 means update. Change I to new value v. I minus minus because I want indices from 0 to n minus 1. Else it is some query. Like that. And n not declared. Well, let's pass n or make it global. Shadowed. Okay. This is another way to iterate or to repeat something q times. This works in C++. Did I already copy it? I'm not sure. Works. And gets accepted. Right. Update here is modifying a leaf and then updating everything on the path to the root from this leaf. Updating a node, it means to again say the value here is the sum of 2 values in the children, 2 values of children. This is the iterative version, it's not recursive. But we can also do it recursively by following the same pattern as we have here. This was function f, right? This maybe should be a better name, like getSum. But let's copy it and create a function, what is it? Change. And it will follow the same principles, it will just not return anything. Return nothing, here same stuff, but also we get as the last argument the new value, we get and we pass that value, and with this range, this time it will be range of size 1. So query will just say modify this single element, the leaf, to some new value. And in this case, when can this be true? If query says modify position 3 to this new value v, then the range query low, query high, it will be just 3, 3. When can this happen? When can it happen that range 3, 3 contains inside range node low, node high? Only in one case it can happen, when node low and high are both 3. So just for a leaf. This will happen only once and it will be a leaf. I am a leaf. And we should then do of tree of node is v, and return. Familiar with recursive segment trees? Should I switch to iterative? No, and I explained why not. Because recursive version is more general. It can handle everything, including harder problems. Okay, we have this, but that's not everything. This is almost everything, but not everything. If we just did this instead of the iterative version, then we would only modify the leaf and we wouldn't modify other nodes. For everybody else on the path to the root, we need to say, hey, you are again the sum of your two children because one of your children modified, like it has a modified value. And then let's see what should be the order of steps. Like this 5, let's say. The 5, it says, hey, my children, if you are responsible for a range from 3 to 3, then update yourself, sure. Then maybe some value here inside will be modified. And only that, after my one child is modified, I here should put a new value as the sum of two children. So after I go and sorry, where is it? Yeah, change. This time I shouldn't return. So I should just run it for my left child. Run it for my right child. And after they are done, and one of them gets modified, I should here say tree of node is the sum of two children. That's a general recipe to do something in a binary tree, to do kind of anything like a bottom-up DP, dynamic programming. Go to left child in a binary tree, go to right child. Both those are computed, they have proper values now, and I now have the sum of values of my two children, because only now those are properly computed, updated. And this is recursive version. What do I need to run now? I need to run change, starting from the root, for interval from 0 to n-1, like from 0 to 15. Query. Query is just, what am I doing? No, I'm modifying the update, sorry. For the root from 0 to 15, and query low, query high are both I, and we change to this value v. So it says modify this range from I to I to this new value v. This is again the blue range corresponding to saying what the root is responsible for. Oh, and I should run function change here, not f. Let's submit this again. And you know, this version is a little bit more complicated, I would say. This one, where we recursively do an update of a single point. But as I said, recursive stuff is more general. To be honest, when I deal with such a problem, then I almost always just update like this iteratively. So I go to the I update proper leaf and then I handle path to the root, because well, this takes less than a minute to implement and this takes strictly more than a minute. But I already told you there are some harder problems that can be solved only with recursive implementation of segment trees. Cool, accepted. Divide and conquer plus dp equals segment tree. Kind of, I would say that segment tree is something like persistent divide and conquer. Yes, Rastafa, it will be on YouTube. All my streams are later on this YouTube channel. What else is worth noting? Well, we can combine those two into one. let's actually do that now. You see, we did almost the same thing in both cases, right? So what about I try to do it as one function? This function should be the combination of two. And what it needs is here to say, let's say that if v is -1, if v is -1, then it means that v doesn't matter. Like, this can be called for an update or a query about the sum in range. Then if v is positive, not -1, then I will actually use it. So if v is not -1, tree of node is v. And I can always return tree of node. It doesn't hurt that I always compute the sum in the range. And what else is needed is here I need to say tree of node is the sum of two children. Sorry about indentation. Done. This is kind of like super function that is able to handle both. Oh, and we return the sum. Here at the end, what we did is, instead of immediately returning the sum, I saved it for a moment. Then I updated my node using values in my two children, because they are possibly updated. Well, that only happens if v actually is not -1. Whatever, we can do a little bit extra work instead of making ifs that would anyway take time. And return the sum that you saved here. Now, when you want a change, you just run this function f for those same arguments. And if you want the sum, the range sum, you just put -1 as the last argument. What's wrong? Too few arguments. I'm not passing v. Submit once more. And this is not the fastest possible, this is not the best possible running time, because we do unnecessary stuff. If you want your program to be really as fast as possible, because you are afraid about time limit, then you shouldn't do what I did here. You shouldn't have one function. You should have two separate functions, and they, are optimized towards a different thing. This one both tries to update and computes the sum. But the sum is not required if that's an update. And updating the value is not required if we just want to ask the sum. It's okay here to say if v is not -1, so actually if we have an update, only then we do this. But that's not necessary, so why bother? The difference in running time is maybe 5% or so. It's negligible. All this code available in some repository later? Yes, it will be. Okay. Now that we are done with the code, I will remind you what happens. No, you cannot say this at any point, because tree of node, it should represent the sum of all values below, while sum is the sum of values from the query. And that's very important, so I will explain that with a drawing. Let's say that you have this. In the root, we have a query about this range. The root asks the left child, hey, what's your sum of values in this yellow range? And this guy returns back 2, because it computed recursively that here in this yellow range we have 2, but only looking at this subtree. The right child, it returned to us 1. Now, this line tree of node equal to sum, it would set the value here to 3. but we shouldn't mistaken the returned value, which is just what's here in the yellow interval and should eventually be printed to the output. We should not mistaken that with the value here, which should represent the sum of everything below. Those are two different things. But Olimpo, I understand the question. It's quite natural to think so. Okay. That's how you can implement segment tree. And one last thing I want to show is what happens when we have a range update. And that's here. This new problem says process Q queries of the following types. Increase each value in range AB by U, and what is the value at some position. Oh, and before I do that, obviously if the problem is about range minimum query, like if you need to find minimum in an interval, then here you will not have the sum, you will have the minimum of two values. If the left child told you, oh, my minimum is 5, right child told you my minimum is 7, then you should return minimum of 5 and 7, obviously. And same in merging, when we have this, when you build a tree. If you want to have tree to compute minimum in interval, always for a node, you will see what is value in left child, in right child, and you will take the minimum out of them. The only thing that will change is that here instead of the sum we will have minimum, here instead of the sum we will have minimum, and here instead of the sum we will have minimum. I think those are the only three changes that you should do to solve the problem of getting range minimum query, of answering range minimum query. Time complexity of f. Okay, good question. Let's talk about time complexity. I need this big drawing. You remember how I told you at the very beginning that stuff is easy for a prefix? If you get a query about prefix, then we can as well just get a binary representation of that. It will be similar here, just twice more. If you have a query about this range, then what's the number of nodes that we will use in our recursion? We remember that if some node is completely inside the interval, like this one, 6, we will not go recursively down, because we just will take the value 6 and that's it. Also, why is this line so long? How do we use this fact? Well, the root will run recursively for both children, and for both children I claim that what we really have here for the right child is query about the prefix. Like if you just focus on this part, you got query about prefix. And from this we already know that our code will do something equivalent to looking at binary representation of the length of this prefix. In this case, length of this prefix is 7, so it will use the sum of 4 values plus the sum of 2 values plus the sum of 1 value. The sum of those three numbers, that's the sum of 7 elements from our prefix. And it's not that we directly jump there, we need to go through those kind of temporary vertices. Well, everything here will be visited as well. But it will give us only twice logarithm instead of logarithm. Everything that will be visited, that we will ever touch a vertex, and that's the very kind of official and formal proof. If you look at the final here position 14 and you look at its path in green, path from 14 to the root, then we can only really visit those vertices with some very small exceptions. If I ever get to the left from this green path, like here, I will immediately stop, because every such node, it needs to correspond to something, like it needs to be completely inside the query. Same here. We go from the green path to the left. Well, this is inside the query, the yellow query, and we will not go deeper down. So always when we are in green vertex, maybe we have one extra operation from this going to the side, but that's it. And if we went from green vertex to the right, like here, then we are outside of the yellow interval. So we will only visit those green vertices, same on the left. You can draw here a path from the leftmost position in yellow interval, and we can always say that we will visit our recursion will visit green vertices, and also from each of them it will try to go to the other child, but if it's child towards the middle of the yellow interval, we will immediately stop here, we will not go further down. So it's one operation, not extra log. And if we go outside of yellow interval, so we will go to the other child to kind of get outside of the range of this yellow madness, like here, then it will immediately stop, because we will see that this is outside of yellow query interval. The size of yellow path is twice log, and from each of them we will also visit an extra child, so we can say times 2. This is the complexity of our recursive function, because this is the number of nodes it will visit. How can we avoid padding for odd n? Doesn't matter. Many people avoid padding, and it's possible, but I don't, and it was never an issue for me. I always pad to the power of 2. Size of a tree is twice n, where n is power of 2. And I told you at the very beginning that we don't really need this. What really is needed is to say, well, sorry, that we don't really need to push back all those zeros, as long as later you here will do that. But that's not really very helpful, or it's not important. So here I just mean this. You have an array of size 5. You still need to size the next, you still need to find, at least in my implementation, the next power of 2, that's 8. You will resize 3 to be twice 8, because you need indices from 1 to 15. But it's not that you need to here push back zeros to the array, because you will not try to access those zeros anyway. Well, you need them in a tree. But the tree is by default filled with zeros. So, if we remove this, then the code does something like that. Let's say we have a sequence, and the sequence is 5, 6, 7. N is 3. Well, my code will find the next power of 2, n is 4. It will build a tree, and it will assign twice n, right? So this will be able to use indices from 0 to 7. And for me, those indices, they will relate to this kind of binary tree. Again, the root is 1. That's in blue. And values 5, 6, 7, they start here. 5, 6, 7. Here by default is 0, whatever. Then there you will put 13, there you will put 7, and here 20. It's not that I needed to here push back 0. But what you see on the screen is exactly what my code will do for the starting sequence of 5, 6, 7. And then if they tell me to modify the second value to 6, then it will modify value 6, 13, and 20. When I do resize in C++, this fills with zeros by default. You don't need to run assigned. I rely on that here. What else I should tell you? Well, if we here dealt with the range sum query, and I was outside of the range, I here return 0, because 0 is neutral element. If I deal with the sum and I say, oh, I don't have anything for you, my parent, so I will just give you 0, and you can sum up something legit with 0, sure. But if you have range minimum query, you should here return infinity. So it wouldn't affect the answer. If you return 0 for something that doesn't really have intersection with yellow query interval, then 0 would become the final answer, because you will take minimum of 0 and something. If you need to find minimum in interval, you will need to use infinity as the default value. All right, one last thing. How do we increase value in a range by u? And what is the value at position k? So let's solve this new problem. I don't need really a drawing, do I? I guess I need to do that. Well, this is the opposite kind of problem. And in this problem, when you have a segment tree, and there is an update where they tell you here in this range increase everything by +5, and you don't want to do it linearly by iterating over those elements, it's okay to just add +5 here and there in those two nodes. Just like if they ask you about the sum of values here, you would take the sum of those two nodes. Then here, when you want to increase, you will increase here and there. And then what happens when you have a query? Then there comes a query and they ask us, what's the value at position k? Well, this will be the original value here plus whatever is added. And that's whatever is added here, but also in the path to the root. Because +5 here means exactly that somebody before added +5 to this whole range. In particular, it added something to me. So this +5 means that it's actually +5 for those two leaves. So whenever I have a query about a position, I need to grab the sum of values in the path to the root. How will this look like? If something is completely inside, let's say that v not -1, it will mean that we need to increase this time. And what else? If we have a query, so if v is -1, then we take the sum. I'm sure we're missing something. I think we need to do this, don't we? So we ask our children to provide us something, but then not only I return this sum from children, but I also take myself. And this way we will grab everything in the path to the root. Queries are 1ABU, I'm subtracting 1 from the range to use indices from 0 to n minus 1, from A to B modified by U. This is update, and this is value at position k. Again, subtract 1 and ask about the range from k to k. Increase by -1. This will denote that I actually don't want to increase. I hope I didn't mess it up. I did mess it up. Oh, because right now I shouldn't really do this. This part, so far, it computed sums of values in every node. Same here, I don't want that. I commented out those two parts, where in every node I wanted to keep sum of values in two children. I don't want those sums. And now it worked, 5 and 6. So the values in leaves, they represent just original values from the sequence. And then whenever we have some increment in a range, it will do this plus x for some single nodes. And later, when I have this yellow query, hey, doesn't work. Why? Well, whatever. Whenever I have this yellow query, if it's kind of below some plus 5, it will catch this plus 5 while going to the root. Alright, and let's fix this because it tells me it's bad that I'm using the same variable name, a and a. Let's use low and high. Low, high, low, high. And submit. All the codes will be in GitHub repository. If you're later watching on YouTube, link is in the description. Why not use tree of size n? Well, I showed you my solution. In my solution, I heavily rely on powers of 2. It's just then easy to say what's going on. It is possible not to use power of 2. It's possible to just use n. But in my opinion, it's more complicated to then debug. And while here, you know what's happening. You know exactly how the segment tree looks like. So I showed you my implementation of segment trees. It's not the only one, but it's something I used for past 10 years, and it served me well. We can use Fenwick. Fenwick has subset of functionality of segment tree, so I will, okay, chat, guess how many times in my life I used Fenwick or BIT. That's a puzzle for you. I used BIT/Fenwick. The first correct answer is Malvika, 0. I solved in my life thousands of problems, hundreds of them required segment trees. I never used Fenwick trees, which I hope shows you that they are not necessary to know. That being said, how many problems I saw that require BIT Fenwick? The answer to this is not 0, it's actually 1. I was once an organizer in a contest where the space requirement was very small, like 4 megabytes or something. N was up to say 10 to 6 and memory is 4 megabytes. And you needed int, and then segment tree is twice too big, and they required Fenwick tree just because it's twice smaller in terms of space, the memory usage. How many problems I saw in my life that really required Fenwick rather than segment tree? Only 1. There are for sure some cases where Fenwick is better because it's a bit faster, but it never happened to me that I needed to use it to get accepted. Like, really think about this when you are considering whether to learn Fenwick trees. But I understand if you want to use them. Though I'm telling you that I solved a lot of problems in my life and never I needed to use them. I know how Fenwick trees work, I just never implemented them. All right. The stream is over now. I wanted to show you the implementation. I showed you the implementation. Hope you now will be able to write something like this from scratch. A general advice: when you learn a new topic, including here the implementation, you should then, at least once, solve a problem from scratch, not looking at the notes, not looking at my implementation. Maybe if you really need to, then yeah, look at some particular part. But if you really understood what happened, then you should be able now to reconstruct it. And what about you go to CSCS problem set, range queries category, and you should solve, for example, dynamic range minimum queries. Or XOR should be very easy, it's as easy as sum, but minimum queries, if you want a harder problem, then I think forest or hotel, those can be solved with segment trees too. Did I win the t-shirt? No, I bought it because I saw it, that's it. Coding game, I'm skipping this coding game contest, so maybe next half a year. Forest isn't segment tree. All right, yeah, forest isn't. Hotel is. Hotel can be solved with a segment tree, but that's less trivial. But you should do range minimum queries as, okay, let's say, a homework. Preferably don't copy my code, write it yourself, but you can access my code in GitHub repository, link on YouTube in the description. And harder homework, if you're more familiar with segment trees, if you really understand them, then it's hotel queries. How many t-shirts I won? 200? Yeah. More than once in my life, I needed to throw away t-shirts, and I had more than 50 of them that I threw away. By throw away, I mean, threw in some bin where you donate clothes to charity. I didn't put them in a trash bin. All right. Thank you all for watching, and bye-bye. I don't know when I will cover lazy segment trees. See ya.